Why does a nail hammered into an oak beam 500 years ago look as if the blacksmith had only just finished working on it yesterday, while your car starts to rust before the warranty has even expired? We are accustomed to believing that technology is advancing inexorably, that each new decade makes materials stronger and more durable. But 21st century metallurgy faces a paradox. The more perfect our processes become, the faster the results of our labor die. Modern factories melt thousands of tons of steel in a matter of hours, creating a material that is perfectly smooth, predictable, and frighteningly short-lived. Meanwhile, iron forged in primitive village furnaces, without electronics or calculations, survives for centuries. It stands in old bridges, hidden inside castles, concealed in church vaults, resisting water, wind, and time. Watch the video to the end, and you will learn why the perfect purity of modern steel makes it as weak as paper, how primitive, dirty technologies gave ancient metal almost immortality, and whether you can buy steel today that will outlive your house. What if I told you that everything you believed about the purity of metal is not true? Modern metallurgy is obsessed with the idea of purifying alloys of any foreign inclusions for the sake of uniformity. We consider slag and impurities to be enemies that weaken the structure and spoil the appearance of the product. Medieval craftsmen did not have the ability to completely separate iron and waste rock in their bloomery furnaces. As a result, thousands of microscopic fibers of silicate slag remained in the metal structure. These inclusions, which today would be considered a defect, acted as reinforcing threads in a composite material. They created a complex, layered structure inside the metal bar, resembling wood. It was this dirty structure that became the first line of defense against corrosion, which modern steel lacks. When rust begins to eat away at modern homogeneous sheet metal, it encounters no resistance and penetrates deep into the metal. In medieval iron, corrosion encounters a barrier of chemically inert glass, the very same slag. It has to find detours, meandering, which slows down the destruction process tens and hundreds of times. It's like how water easily passes through sand, but gets stuck in layers of clay. It turns out that a technological shortcoming became the main advantage of the material in the long term. The process of obtaining wrought iron was incredibly laborious and required enormous physical effort from the craftsman. The iron sponge, saturated with slag, had to be repeatedly hammered to squeeze out the excess and compact the mass. With each blow of the hammer, the structure of the metal became denser and more oriented. This not only shaped the bar, but also created a unique internal architecture of the material. The craftsman literally kneaded the metal like dough, distributing protective layers throughout the entire volume. No modern rolling mill can reproduce this chaotic but salvific pattern. We are used to thinking that handwork is only about aesthetics, but in this case, it was a functional necessity. Each blow of the hammer closed the pores through which moisture could penetrate. The blacksmith felt the metal, understanding where to strike harder and where the metal was still raw. This created individual protection for each nail, each bracket, and each bar of the grating. Modern conveyor belts stamp out millions of identical products with identical defects. The ancient craftsman made each soldier of his iron army unique and ready for eternal defense. In addition, the raw materials for iron production in those days were fundamentally different. The bog ore, often used in Europe, contained a specific set of elements. These natural additives were transferred to the metal, changing its properties at the chemical level. We spend billions on alloying steel with chromium and nickel, trying to cheat nature. Medieval craftsmen used what was under their feet and achieved results that are unattainable for us. Nature itself suggested the composition of the eternal alloy. One only needed to know how to extract it. It is important to understand that the survival of metal is not luck, but the natural result of a chemical lottery. Phosphorus, which often entered the metal from ore or fuel, is now considered a harmful impurity. It makes steel brittle in the cold, which is unacceptable for modern bridges and rails. However, in ancient cathedral grills and ties, phosphorus acted as a preservative. It created a film on the surface that stopped oxidation at the very beginning. We sacrificed durability for mechanical strength and flexibility. Modern steel is a solution of carbon and iron, as homogeneous and predictable as possible. We know exactly how it will behave under load, but we also know that it will die without paint. Medieval iron was a living organism with its own veins and arteries of slag. It may have been less resistant to tearing, but it knew how to heal its wounds. The oxide film on such metal held faster, without flaking off. It was armor grown by the metal itself, not artificially applied to it. Ancient iron can be visually distinguished from modern iron even by the nature of its corrosion. Old metal darkens, becomes covered with a noble patina, but retains its shape for centuries. A modern steel beam swells, flakes, and turns into red dust. We have created a consumer society even in the world of metals, where things are not required to outlive their owners. The Middle Ages lived in terms of eternity because extracting every kilogram of iron was a feat. Throwing away or replacing a rusted part was an unaffordable luxury for the economy of the time. Today we try to imitate the properties of ancient iron by creating weather-resistant steels such as Corten steel. But even these require strict operating conditions and alternating cycles of wetting and drying. A medieval nail in the wall of a castle required nothing more than to be hammered in and forgotten. It simply did its job, ignoring rain, snow, and the changing of eras. This silent superiority of archaism over progress makes us think about the correctness of our path. Do you agree with this? Please tell us what you think about this. Every opinion is valuable. Are you ready to learn the truth about what kills modern metal at the smelting stage? The fundamental difference between the metallurgy of the past and the present lies in the fuel used by the craftsman. For thousands of years, charcoal was the only source of heat for smelting ore. This fuel was incredibly clean from a chemical point of view, containing almost no harmful impurities. The forests of Europe burned in charcoal pits to give life to metal, free from the main disease of modern times. Charcoal gave off heat but did not contaminate iron with elements that cause accelerated corrosion. The situation changed dramatically with the onset of the Industrial Revolution and the transition to coal and coke. The Earth's interior contains not only energy, but also the periodic table, including sulfur. Sulfur is a real poison for iron, making it brittle and prone to oxidation. When coke burns, sulfur is eagerly absorbed by molten metal, becoming an integral part of it. It is almost impossible to remove it completely. One can only reduce its concentration to an acceptable level. But even small doses of sulfur trigger processes within the metal that lead to its destruction. Charcoal, on the other hand, often enriched the metal with useful elements transferred from living wood. Tree ash contains potash and other substances that could act as mild fluxes. Smelting with charcoal took place at lower temperatures than in modern blast furnaces. This meant that iron did not become saturated with carbon to the point of becoming cast iron in an instant. The process was slower, allowing the craftsman to control the birth of the metal at every stage. It was like cooking, where not only the ingredients were important, but also the heat. Modern coke provides the enormous temperatures and melting speeds required for mass production. We gain in quantity, flooding the world with cheap steel, but lose in the quality of the material itself. Sulfur in steel creates microscopic stress points around which corrosion begins. In the presence of moisture, these inclusions turn into miniature galvanic cells. Steel begins to devour itself from within, even under a layer of paint. Ancient iron, smelted over a clean fire, is devoid of this mechanism of self-destruction. In addition to sulfur, coal contains a whole range of other impurities, from arsenic to heavy metals. All of this, to one degree or another, is transferred to the final product, changing its crystal lattice. Old metallurgy was environmentally friendly in relation to the material itself, although it was destructive to forests. We have learned to preserve forests by switching to fossil fuels, but we have condemned metal to a short life. This is the price civilization has paid for the ability to build skyscrapers and giant ships. Scale has killed the individuality and durability of the material. It is interesting to note that even in the 19th century, the best grades of steel continued to be made using charcoal. Ural manufacturers long resisted the transition to coke precisely because of the decline in product quality. Old sable metal was valued in Europe precisely for its purity and softness, born of the forest. But economics are relentless. Coke is cheaper, more accessible, and more efficient for large volumes. Quality gave way to profitability, and we finally entered the era of sulfur metal. The effect of fuel on the structure of metal can be compared to the effect of nutrition on human health. Medieval iron was fed with organic, pure products and grew healthy. Modern steel is fed on fast food from fossil fuels, full of chemical additives. It looks powerful and strong, but inside it already has diseases that will kill it prematurely. We have learned to treat these diseases by alloying, adding vitamins, but we have not eliminated the cause. The basis of modern metal is inherently flawed because of the way it is produced. Even the air supplied to the furnace played a role in shaping the properties of the metal. In old low furnaces, the metal had less contact with nitrogen in the air. In modern converters, oxygen and air blowing saturates the steel with gases. Nitrogen and hydrogen make the metal brittle and prone to aging. We combat this vacuuming by complicating technologies to fix what we ourselves have ruined. Ancient processes were more harmonious and naturally avoided these problems. Our dependence on fossil fuels has made our civilization fast but fragile. We create things that need to be constantly replaced, driving the flywheel of consumption. If we built bridges out of metal similar to that used in the Middle Ages, they would last 1,000 years. But then metallurgical plants would be out of work within a generation. Perhaps the short life of steel is not a bug, but a feature of the modern economy? The transition to coke was a point of no return, dividing the history of metal into before and after. We gained the ability to reinforce concrete and build railways encircling the globe. But we lost the magic of living metal, which could withstand time on its own. Now metal is disabled, needing crutches in the form of paint, zinc, and electrochemical protection. Do you think technological progress was worth the loss of quality in basic materials? Want to know a secret that will change your perception of strength? If you look at a cross-section of a medieval iron rod under a microscope, you will see not a homogeneous field, but something amazing. The structure of this metal is more like a dense bundle of ropes or fibers of high-quality wood. This is the result of how they processed crucible iron, the primary lump of iron extracted from the furnace. Blacksmiths hammered and folded the metal hundreds of times, stretching it into long fibers. The slag inclusions we talked about earlier were stretched along with the iron, forming the finest glass threads. This fiber structure gave the metal unique mechanical anisotropy. Along the fibers, such metal was incredibly strong in tension, just as it is difficult to break a wooden slat lengthwise. Across the fibers, it could be softer, but craftsmen used this property to their advantage. They forged products so that the lines of stress coincided with the direction of the fibers. This required a deep understanding of the internal nature of the material and intuitive knowledge of materials. Modern castings have a granular structure that is the same in all directions but lacks this internal reinforcement. When a crack appeared on the surface of such fibrous iron, it could not spread instantly. The crack rested against the slag fiber, changed direction, lost energy, and stopped. In modern steel, a crack, finding a weak spot, penetrates the part like lightning. That is why old anchors and chains could deform and bend, but not break suddenly. They warned of overload by their appearance, giving time for repair or replacement. Sudden brittle failure is the scourge of modern high-strength steel. Imagine the difference between monolithic glass and plywood glued together from multiple layers. Ancient iron is metal plywood, a composite material created by human hands. Each layer was separated from the other by a microscopic layer, creating a barrier to destructive processes. This made the metal ductile, able to absorb the energy of an impact without breaking. For combat weapons and armor, this was a critically important quality. Interestingly, this structure was not the result of precise scientific calculation, but a side effect of the technology. The craftsmen simply tried to remove excess slag by repeatedly hammering and folding the blank. But it was this action that charged the metal with durability, turning a disadvantage into an advantage. The more effort the blacksmith put in, the more he heated and hammered the metal, the better the structure became. The iron absorbed time and labor, only to give them back in the form of centuries of service. Modern rolling mills form texture, but it is no match for forged fiber. Rolls simply flatten the grains, but do not create isolated protective layers. We get a sheet of metal that behaves predictably, but lacks character and hidden reserves of strength. The Industrial Revolution replaced the quality of the internal structure with external volume and mass. We rely on thickness, where our ancestors relied on the ingenious structure of the material. The uniqueness of each piece of iron in the Middle Ages meant that each product was treated individually. The craftsman knew where the fibers would go in a door hinge and where they would go in a knife blade. It was programming the properties of the material on a physical level without computers or formulas. A mistake in the direction of forging could cost a warrior his life or a building its strength. Therefore, craftsmanship was passed down from generation to generation as the greatest secret. Corrosion in such metal also behaved differently, spreading along the fibers rather than in spots. This often caused old iron to delaminate like old wood, but it retained its load-bearing core. The surface layers could fall away, sacrificing themselves, but the core remained intact. Modern rust works like a bark beetle, eating away at the metal chaotically and deeply. We have lost this effect of the outer layers sacrificing themselves to preserve the essence. Even today, restorers working with ancient monuments are amazed at the preservation of metal under a layer of dirt. Once the centuries-old patina is removed, living, shiny metal is revealed underneath. This is evidence that the structure of the material was sealed conscientiously. Modern rebar and concrete rots away completely, leaving nothing but rusty stains. We are building a disposable world out of disposable metal. Medieval iron architecture is a hymn to human patience and labor. It reminds us that the most reliable things are created slowly, layer by layer, blow by blow. In our pursuit of speed, we have simplified structures, forgetting that complexity is the key to survival. I urge you to like this video if you also appreciate the quality of the old masters. And don't forget to subscribe to the channel so you don't miss any new videos. Are you ready for the shocking truth about waste recycling? We are proud to have learned how to melt down old cars and refrigerators into new steel, saving the planet. But there is a dark side to this coin that is not usually mentioned in advertising brochures. With each recycling cycle, so-called stray elements accumulate in the world's steel, the main one being copper. Copper enters the furnaces from old wiring, electric motors, and electronics that could not be completely separated from the steel scrap. And while copper is gold for electrical engineering, for steel it is a slow death. Copper does not burn out during remelting. It remains in the steel forever, accumulating with each passing decade. Today's ordinary construction steel contains much more copper than steel smelted 100 years ago. This leads to a phenomenon known as red brittleness. The metal begins to crack during hot working. But even worse, copper changes the electrochemical potential of steel, making it more vulnerable to corrosion. We are literally poisoning our own metal in an attempt to be economical and environmentally friendly. Medieval iron was always extracted from primary ore and was pristine, free from this technogenic virus. In addition to copper, modern scrap metal contains tin, antimony, and other elements from solters and coatings. This chemical cocktail makes the structure of modern steel heterogeneous at the atomic level. On a microscopic scale, galvanic couples arise which begin to work as soon as water comes into contact with the metal. The steel begins to generate electricity, dissolving itself in the process of electrolysis. Ancient iron was chemically simple, boring, and therefore long-lived. There were no internal conflicts between dissimilar elements in it. The problem of impurity accumulation is a time bomb for all of modern civilization. We do not know how to effectively remove copper and tin from molten metal on an industrial scale. This means that the quality of ordinary steel will steadily decline, and the rate of its corrosion will increase. We are creating a closed cycle of degradation, where each new car is made of slightly worse metal than the previous one. The Middle Ages did not know the concept of recycling on an industrial scale. Each product was created from scratch. This ensured that the karma of the metal was reset to zero and guaranteed its purity. We are trying to combat this by diluting dirty scrap with pure iron from direct reduction, but this is expensive. Economics pushes manufacturers to use as much cheap scrap as possible. As a result, we have rebar that can crumble to dust in 30 years. For a medieval builder erecting a cathedral for centuries, such material would be nonsense. They built for their grandchildren. We build until the first major renovation. Even the radiation background of modern metal differs from that of ancient metal. Steel smelted after 1945 contains traces of radionuclides from the atmosphere that got there after nuclear tests and accidents. For high-precision physical instruments, steel from sunken ships from the pre-atomic era is now being sought and raised from the bottom of the sea. Only this ancient iron is pure enough for science. It is ironic. To look into the future of science, we need iron from the past. The paradox is that our technological power has become a source of our weakness. We can split an atom, but we cannot easily and cheaply extract copper from molten steel. A medieval blacksmith did not have these problems because electrical wires simply did not exist in his world. His limitations were his salvation, while our omnipotence has become our trap. The purity of ancient metal was natural, while the purity of modern metal is an unattainable ideal. Stray elements make steel capricious during welding and heat treatment. Engineers have to build in huge safety margins to compensate for this uncertainty. We use more metal to compensate for its low quality. Medieval structures often appear delicate and light because the craftsman trusted his material. He knew that there were no treacherous, non-ferrous metal inclusions inside the rod. The globalization of the scrap market has led to impurities being mixed together around the world. Steel from an American car can end up in Chinese rebar and then in a Turkish pipe. We have averaged out the composition of metal across the planet, making it equally dirty everywhere. Local deposits with unique ore properties, as was the case in the Middle Ages, no longer play a role. We have lost the geographical uniqueness of iron, turning it into a faceless commodity. Perhaps in the future, we will have to extract iron from old landfills, like ore, by developing purification technologies. But for now, we continue to accumulate mistakes, making our world less and less durable. Ancient iron teaches us that sometimes less is more. What do you think is more important, environmentally friendly recycling or the durability of materials? In majestic Gothic cathedrals, with their spires reaching for the sky, iron plays the role of an invisible skeleton. We are accustomed to admiring the stone carvings and stained glass windows, forgetting what holds this mass together. Huge iron brackets, ties, and pins pierce the masonry, taking on enormous tensile loads. Stone works perfectly under compression, but cannot withstand tension, and this is where metal comes to the rescue. If this iron behaved in the same way as modern steel, the cathedrals would have collapsed long ago. The main enemy of stone is rust, which increases in volume several times over as it forms. A rusting modern pin inside a stone block acts like a jack, tearing the stone apart from the inside with tremendous force. This phenomenon is called the iron cancer of architecture, and it destroys many restored buildings. However, medieval staples have often coexisted peacefully with limestone and marble for half a millennium. The secret lies not only in the properties of the metal itself, but also in the way it is installed. Medieval builders filled the iron elements in the stone with lead. The lead not only sealed the joint, preventing water from entering, but also served as a soft buffer. It allowed the iron to move slightly during thermal expansion without transferring stress to the fragile stone. In addition, the lead created an alkaline environment at the contact boundary, passivating the iron surface. It was a brilliantly simple system of electrochemical and mechanical protection. Even without lead, wrought iron rusted differently without creating such expansion pressure. Its layered porous oxide crust was less aggressive toward the surrounding material. Rust penetrated the metal rather than pushing it outwards, as is the case with dense modern steel. Thanks to this, the stone remained intact and the structure retained its monolithic integrity. Before the fire, Notre Dame Cathedral in Paris concealed hundreds of tons of iron, which was part of its original design. Builders of that time understood the compatibility of materials on an intuitive level, based on centuries of observation. They knew that bare iron and stone did not get along and looked for intermediaries. The use of sulfur, resin, or lead to fix metal was the standard, not the exception. Today, we often simply drive a steel anchor into concrete, relying on chemical additives. We have simplified the installation technology, but at the cost of losing the reliability of the joint. Iron in cathedrals often did the work during construction, holding up unfinished arches. After the masonry was completed, it remained inside, becoming passive insurance against earthquakes or hurricanes. It was a hidden reserve of strength that was activated only at a critical moment. Many of these elements were discovered only during modern research using X-rays and metal detectors. The craftsmen did not boast about the iron. They hid it like bones under the skin. Interestingly, in some cases, iron was deliberately left exposed, creating decorative grills and gates. And even here in the open air, these elements demonstrate enviable durability. The secret often lay in the finishing: bluing, oil blackening, wax coating. Blacksmiths cooked finished products in oil, creating a durable polymer film on the surface of the still hot metal. This method of preservation was simple but incredibly effective. We often underestimate the scale of iron use in the Middle Ages, considering it the Stone Age of architecture. In fact, great cathedrals are hybrid structures, precursors to modern reinforced concrete structures. It's just that the proportion of materials was skewed towards stone. Without confidence in the durability of iron, architects would not have dared to experiment so boldly with height and light. Iron gave them the freedom to create, knowing that their creations would not crumble. Today's restorers face a dilemma. Should they replace old iron with modern stainless steel? Stainless steel is eternal, but it has a different coefficient of thermal expansion and is too rigid. Introducing a foreign modern material into the body of an ancient building can do more harm than good. Old soft iron lived in harmony with stone, breathing in unison with it. Modern alloys are rigid prostheses that can be rejected by the organism of the building. The history of iron and stone is a history of symbiosis, which we have forgotten how to create. We are used to breaking the nature of materials, forcing them to work together with the force of glue and anchors. The ancients sought harmony, selecting pairs that would not kill each other. This lesson in mutual respect for materials is relevant for any engineer or builder. Are you ready for the shocking truth that rust can be a salvation rather than a destruction? In our understanding, rust is an unambiguous evil, a sign of decay and neglect. We spend billions fighting it, cleaning, painting, and varnishing every inch of steel. But for medieval iron, corrosion often became a protective suit. There are two fundamentally different types of iron oxides: loose, red hematite, which we see on old cars, and dense black magnetite. Ancient iron, due to its chemical composition and impurities, had a tendency to form magnetite. This black, hard crust clung tightly to the metal surface, blocking access to oxygen. This is similar to how aluminum is instantly covered with an oxide film and stops oxidizing further. Medieval iron was able to passivate naturally, especially if it was kept in stable conditions. The famous iron pillar in Delhi is the most striking, though not the only example of this phenomenon. Modern carbon steel forms loose, porous rust that absorbs moisture like a sponge. This wet layer becomes a catalyst for further destruction, eating away at the metal layer by layer. The oxide film on modern steel constantly flakes off, exposing fresh metal to new attacks. It is an endless cycle of self-destruction that cannot be stopped without external intervention. Ancient metal knew how to say stop to corrosion. Phosphorus, which we have already mentioned, played a huge role in the formation of proper rust. The phosphate film acts as a natural primer on which corrosion slides, unable to take hold. In the Victorian era, when phosphorus began to be removed from steel for strength, engineers were horrified to notice a sharp drop in corrosion resistance. They got strong rails that rusted faster than the old, weaker cast iron ones. This was the price they paid for the physical strength of the metal. The atmosphere of the Middle Ages was also different from today's. There was no acid rain or sulfur dioxide from burning coal and oil. In clean air, a protective patina formed slowly and thoroughly over many years. The modern aggressive urban environment attacks metal with acids that dissolve any protective films. We have placed metal in a chemical warfare environment for which it was not evolutionarily prepared. Even the best ancient iron would perish faster today in the atmosphere of a modern metropolis. Interestingly, archaeologists often find iron objects in swamps in perfect condition. In the oxygen-free environment of peat bogs, vivianite, a blue iron phosphate, formed on the surface of the metal. This natural mineral preserved weapons and tools better than any museum varnish. Nature itself took care of preserving the creations of human hands if they ended up in the right conditions. A modern landfill is a chemical reactor where metal has no chance of survival. We try to imitate protective oxides by bluing and oxidizing weapons, but the factory coating is only a thin film that is easily scratched and worn away. The natural patina on antique metal grew over decades, becoming embedded in the structure of the material. It was skin, not clothing. Attempting to accelerate this process with chemicals only produces a temporary cosmetic effect. The paradox of rust teaches us that not all destruction is evil. Sometimes controlled oxidation is the only way to survive in an oxygen atmosphere. Ancient metal colluded with the elements, giving up a small part of itself to preserve the whole. Modern metal tries to resist to the last, but loses the war completely. What do you think? Is rust a beautiful part of history, or is it just dirt? Between the era of medieval blast furnaces and modern metallurgy, there was a short but vivid period, the era of puddle iron. In the 18th and 19th centuries, before the invention of the Bessemer converter, this was the main method of obtaining high-quality structural metal. The Eiffel Tower, that symbol of Paris, was built from puddling iron, not steel as many people think. And that is why it is still standing today, requiring only regular painting but showing no signs of structural decay. Puddling was hellish work. Cast iron was melted in a special furnace, and the worker, the puddler, had to stir this viscous mush with a long crowbar. The goal was to burn off carbon and impurities with oxygen from the air. This required tremendous physical strength and endurance, working in conditions of unbearable heat. But in the process of stirring, the master literally felt the metal, controlling its condition. The metal turned out to be incredibly pure and viscous, retaining that very fibrous structure. Pudding iron became a bridge between craftsmanship and industry. It was already being produced in large quantities, but still retained the human face of manual labor. Every rivet on the Eiffel Tower is made of material that was touched by human hands during its creation. This ensured quality control during the smelting stage, which was not possible with automatic furnaces. The puddler could spot and remove a lump of slag that would have ruined the batch. The secret to the durability of puddle iron is similar to that of medieval iron: purity of the base and the presence of useful slag. It is highly resistant to vibration and metal fatigue, which is critical for bridges and towers. Modern steel is tougher, but it accumulates fatigue faster, suddenly bursting. 19th century puddling bridges still serve on European railways, withstanding trains that have become many times heavier. The decline of puddling began with the advent of cast steel, which was cheaper and stronger. But this strength was deceptive in the context of eternity. We traded viscous reliability for rigid strength. Engineers at the end of the 19th century argued heatedly about which was better: good old iron or the new fashionable steel. Time has shown that the supporters of iron were right about corrosion, but lost the economic war. Today it is impossible to restore the production of puddle iron. The skills in the school of masters have been lost. No one would agree to work in such hellish conditions for manual smelting when there are computerized factories. It is a lost art, like Damascus steel. We can study its chemistry, but we cannot reproduce the process on an industrial scale. The Eiffel Tower will remain a monument not only to engineering, but also to a unique material that no longer exists. The remains of puddle iron are valued by blacksmiths and restorers as much as gold. They look for it in old anchors, rails, and demolished 19th century buildings. It is used to make elite knives and artistic items because it has a unique living pattern. It is a metal with a soul that is pleasant to forge and work with. Modern steel feels dead and dry under the hammer. We will never return to this method, but it is necessary to know about it. It helps to understand why the old world looked and aged differently. The world of puddle iron was a world where metal was respected and its whims understood. In the mid-19th century, Henry Bessemer patented a converter that turned the world upside down. He came up with the idea of blowing air through molten iron, burning off the carbon in a matter of minutes without any fuel. It was a revolution. Steel, which had previously been as precious as gold, became as cheap as dirt. The world got rails, ships, skyscrapers, and weapons in unlimited quantities. But it was this moment that marked the beginning of the end for the durability of metal. The Bessemer process was fast and brutal. It did not allow for fine adjustment of the metal's composition, as puddlers did. Most importantly, it completely removed the slag, making the steel homogeneous and dense. The very protective fibers we talked about at the beginning disappeared. The steel became naked in the face of corrosion, having lost its internal structure. We got a monolith that was strong but defenseless. In addition, Bessemer's converter saturated the steel with nitrogen from the air. Nitrogen dissolved in the metal, making it prone to aging and brittleness over time. The steel became glass-like in the cold, which led to disasters on the railways. For a long time, engineers could not understand why the new strong rails broke more often than the old iron ones. The reason was the speed of production, which did not allow the metal to rest and purify itself. Mass production required standardization. No one cared about the unique properties of each batch anymore. Steel became a faceless commodity, a brand and a catalog. This gave rise to a culture of disposable items. If steel is cheap, why take care of the product? You can just melt it down and make a new one. The era of repair and maintenance was replaced by the era of replacement and disposal. Bessemer gave us quantity but stole the soul of the material. We flooded the planet with steel that starts to rust as soon as it leaves the factory. Our entire civilization is based on an endless struggle against the oxidation of this cheap steel. Paints, varnishes, and galvanizing are crutches for a cripple born in Bessemer's converter. We spend more money protecting metal than we do producing it. Of course, technology has advanced, with the advent of open hearth furnaces and oxygen converters. The quality of steel has improved, and we have learned to alloy and purify it. But the fundamental principle remains the same: liquid phase, complete slag removal, homogeneity. We are following the path of improving Bessemer's idea, not returning to its origins. We are polishing the dead end of the evolution of materials, trying to squeeze the most out of it. Will we ever be able to combine mass production and durability? For now, science is looking for the answer in nanotechnology and composites, trying to artificially recreate the structure we have lost. But nature, as always, has done it better and for free. Bessemer's curse is a lesson that cheapness always comes at a hidden price.
Remarkable. Look at the resonance data here. It defies our models.
The most widespread use of steel today is in reinforced concrete. We hid the metal inside artificial stone, believing it would be safe there. The alkaline environment of concrete does indeed protect steel from rust at first. But as soon as the concrete carbonates from carbon dioxide in the air, the protection breaks down, and then all hell breaks loose. The rusting reinforcement expands and tears the concrete from the inside. Modern buildings, bridges, and overpasses have a design life of 50 to 100 years. After that, they require major repairs or demolition. Compare this to the Roman Pantheon, made of unreinforced concrete, which has stood for 2,000 years. We have introduced a mortal element into eternal stone, modern steel, and thereby shortened the life of buildings. We have created suicidal structures with a built-in time bomb. Medieval builders also used iron and stone, as we have discovered, but they did so more intelligently. They did not create a single composite where the materials depend on each other. Iron was an auxiliary, not a primary load-bearing element. In reinforced concrete, steel takes on all the tensile loads. If the reinforcement rots, the house collapses. It's like a drug addict's dependence on a dose. Concrete without steel is not viable. We tried to use galvanized reinforcement, epoxy coatings, and stainless steel, but this makes construction many times more expensive. The economy dictates the use of the cheapest black steel. We build Khrushchev-style buildings and skyscrapers, knowing that they will become a headache for our great-grandchildren. We are shifting the problem of infrastructure maintenance to future generations. The problem of the concrete tomb is exacerbated by the quality of the reinforcement itself. Made from remelted scrap metal, it rusts faster and more aggressively. We are walling up rubbish in the walls of our houses. This is a time bomb under cities around the world. The collapse of bridges and parking lots is the first sign of a systemic crisis in reinforced concrete. In the Middle Ages, if an iron beam rotted, it could be replaced. In reinforced concrete, replacing the reinforcement is impossible without destroying the structure. We have created monoliths that cannot be repaired. This is a dead end for architectural thought from the point of view of eternity. We build quickly and high, but not for long. Finally, it is worth cooling the ardor of our admiration for the past with a dose of healthy skepticism. We admire the ancient iron that has survived to this day, but we forget about the tons of metal that have rotted away without a trace. We see the survivor's error in action. Only the best, most successful examples remain in museums and architectural monuments. All mediocre, ordinary, and poorly made iron has long since turned into rusty earth. Metal was expensive in the Middle Ages. It was cared for and cherished. A knight's armor was cleaned with sand, and lubricated with grease after each campaign. Tools were stored in dry chests. What we see today is the result not only of the quality of the metal, but also of the quality of its care. If you throw a medieval sword into damp soil next to a modern spring, it may last longer, but it will also perish. Not all blacksmiths were masters of their craft. There were many defects, burnt metal and poor welding, but such products were broken and discarded or reforged even in those days. Natural selection has come down to us, objects that have stood the test of centuries. This distorts our statistics, making us think that everything was perfect in the past. In addition, many of the surviving artifacts were found in unique conditions, inside thick walls, in dry attics, under a layer of fat, or an oxygen-free silt. The environment plays no less a role than the material. We compare the greenhouse conditions of a museum exhibit with the aggressive environment of a road barrier that is sprayed with chemicals every winter. This is an unfair comparison. The history of medieval iron is not a fairy tale about a lost paradise, but a physics and chemistry textbook that we forgot to read. We chose a different path, the path of mass production and accessibility. But looking at the rusty skeleton of a machine and the entire grille of a 12th century cathedral, it is difficult not to ask ourselves, did we make the right turn? We have come a long way from the fiery forges of medieval blacksmiths to the giant converters of modern industry. We have learned that the secret of the durability of ancient iron lay not in magic, but in its imperfection. Slag fibers, phosphorus film, and pure charcoal. What we now consider dirt and defects turned out to be the elixir of immortality for metal. We traded eternity for quantity and structural quality for production speed. It was a conscious choice made by civilization, which allowed us to build the modern world, but made that world fragile and short-lived. The history of iron teaches us that progress always involves compromise. We have gained in strength, but lost in endurance. Perhaps it is time to rethink our approach to materials and try to bring back some of the lost wisdom of our ancestors into technology. After all, if we want to leave something behind other than rusty dust, we should listen to the silent lesson of the ancient masters. What other technologies of the past do you think we have undeservedly forgotten and replaced with cheaper but inferior alternatives? Write your suggestions in the comments and it may become the topic of our next investigation. And don't forget to subscribe to the channel so you don't miss out on new journeys into the history of things.